Okay, so good news. We're gonna play a little Jeopardy. We're gonna play a little Jeopardy here. You guys know about Jeopardy?
You have to ask us a question, right?
Right. So, for example, if these were your, let's make this a little bigger. So, like, if these were your topics. Exactly, it'd be something like that. What you would say is, the answer is, in one translation of Beowulf, he's described as a fiend out of hell and a grim demon. That's the answer. So what's the question? Who is Grendel? Exactly. So that, ding ding, there's a winner, right? Does that make sense? Okay. Just for practice, pick another one, try one more. Which one? What topic are you picking? Yes. What is a manatee? I like it. There you go. That seems right to me. That's what I would guess too. Yep. Okay. Good, good. You get the idea? Okay. Well, I mean, eventually. Eventually. You'll see where I'm going with this, though. Okay. So Jeopardy is a great model for what we're doing from here on out in calculus, right? You thought you were going to have all kinds of fun, which you are, just not the kind of fun you would have anticipated. Yeah. So for example, its derivative is 3x squared. What is x cubed? Very close. Very close. Very close. X cubed is not incorrect, but it's not. There's a more general answer that we'll talk about that'll make sense. But that is one correct answer. That is one correct. Can anybody tell me another correct answer? X cubed, derivative, right? You're just trying to find what could I differentiate.
X cubed plus 7.
You could do that. You could also say what is x cubed plus 7? What's another one?
X cubed plus 3.
What is x cubed plus 3? Okay. How many total answers could you provide?
Infinite.
An infinite number, yeah. Okay, good. Okay, well, how about this one?
What is cosine x? Plus 17.
Plus c, I love it. Plus c, where c is just a constant that could stand for anything. Very nice. Okay, so that is what antiderivatives are, right? If the derivative is f prime of x equals 3x squared, right? What are some questions that would work? Well, what is x cubed plus 6? What is x cubed plus 16? Or more generally, what is x cubed plus c? And this is where mathematicians are really particular about these things, and it's a capital C. It's not a lowercase c. It's a capital C. Stands for the constant of antidifferentiation, or the constant of integration. So can you tell me then, if its derivative is negative sine x, you already got it right. What's the answer? What is cosine x plus c? What is f of x equals cosine x plus c, right? Because the derivative was f prime of x, so the function that we differentiated must have been f of x, right? Okay, give me 1 to 5 on that. Is that all? That's making sense, right? Good. Okay. So then, really what we're setting ourselves up to do is solve differential equations. Well, what's a differential equation? A differential equation is an equation involving at least one derivative, right? So if the solution is 2x plus c, then the differential equation for which this is a solution is the equation f prime of x equals 2. That's the differential equation that we would solve to produce this general solution. Okay? The green statements are the general solutions of the yellow differential equations. Make sense? So we're working backwards here, right? The good news is this is all stuff that you guys learned. You just learned it in a different direction than we're going to approach it from here on out. We're just kind of undoing all the hard work that you did. Now, what do you think is harder to do, to take a derivative or to undo a derivative?
Undo.
Undoing a derivative is a little trickier. than just taking a derivative. And you remember at the start of the year when I had to duck because you were throwing things at me, we said that taking derivatives is really not too bad. It's really not that hard to do because you just follow the rules of differentiation. And by now you're getting to a point where, they're getting pretty easy to do. Some of them are difficult because the algebra is tedious. If you're doing quotient rule problems that involve chain rule, the algebra is tedious and difficult, but the calculus part is really not very hard. There's only a finite number of rules that you use, and you just follow those rules. The algebra can get tough. That's the part that's hard. Okay, so then the solutions of differential equations are just the equations that you would differentiate to end up with the differential equation. So again, there's this jeopardy nature where we're working in reverse. Okay, what does this mean graphically? So here's, if we look at this differential equation, it's a pretty simple one. F prime of x equals 2, right? So the derivative of f of x equals 2. You guys could all tell me, what's the function I would differentiate to get 2 for an answer? Well, 2x plus whatever constant you choose, right? So here it is. This is representative of our general solution. You already told me there's an infinite number of specific solutions depending on the value you pick for your constant, right? Okay, well, here I just gave you some examples. If we start off with the differential equation, this is supposed to be f prime, let's say. F prime of x equals 2x. What are all the possible solutions? Well, those would just be, hang on, what did we start with here? We started with, not that one, did we? We started with f prime of x equals 2, right? And the solutions were f of x equals 2x plus c. This guy. Okay. Well, these are all the lines that have a slope of 2, right? 2x plus c, those would be lines in slope-intercept form with a slope of 2 and a y-intercept of c. So the one most convenient solution is probably the one that has a y-intercept of 0, but that's just one of the infinite possible values of c. I just graphed all the integer values of c and stacked them up. This is what we call a family of curves, meaning the curves, when you look at the general solution of a differential equation, it's a family of curves that all have the same characteristics. Each little specific graph, we call these the trajectories of the family. Each individual trajectory of the family corresponds to one particular value of the constant. Okay, make sense? Did I graph them all? No, I only picked the integer ones. How many solutions are there between c equals 0 and c equals 1? There's an infinite number because there's one for every real number, right? And there's an infinite number of real numbers between 0 and 1. But it's just we don't really necessarily need to graph them all to get an idea what the family looks like. Okay, give me 1 to 5 on that. Is that making sense? Okay. This is a pretty boring family of curves because they're all lines. Let's look at one that's not quite so boring. What about one like that? Now, we already talked about this. You guys told me that if the differential equation is f prime of x equals 3x squared, you just play calculus Jeopardy. What would I differentiate to get 3x squared? X cubed plus a constant. It's going to take a little while for it to graph this one, I bet. We got to be patient, but it'll happen. I'm frying the circuits of Desmos here. Oh, maybe I'm not. Oh, I am. Yeah, see, it takes a while for it to graph this. I clicked the blue button there. Finally, it did. Okay, so why did it take a while? Well, because that's a hard thing to plot. Does it make sense that these are all trajectories of this family of curves? What do you notice about these? How could I get from the red trajectory, which is the one that corresponds to c equals 0, how could I get from that one to this guy right here. Right, you're right, but how could I transform the red trajectory into that blue trajectory? What do I do? You're right. We'll say it again. So to the red trajectory, I just added 1, right? Everybody agree? Right? Isn't that all I did? Right here, the value of c is 0. So this is just x cubed plus 0. This is x cubed plus 1. So I just added 1 to the red trajectory. What does adding 1 to a function do to its graph? It just vertically translates it up by 1. Right? So each one of these trajectories I could generate from the red trajectory just by vertically offsetting it up or down. Everybody get that? Okay. So that's characteristic of a family of curves. They're all identical curves that are just offset vertically by different constant values. Okay? So let's talk about the symbols that we're going to use for this then. So these are a little bit different than what you've seen before. So if I want to write down symbolically this process that we just talked about, we call it anti-differentiation, or more generally, we call it integration. It's for reasons that we'll talk about later. An antiderivative is what we call an indefinite integral. Why is it an indefinite integral? Because it's only true to within a constant. We haven't assigned a value for the constant, right? It's indefinite because we didn't specify what c was. We just left that general, okay? So if we want to take this function, f of x, and we want to play calculus Jeopardy with it, we want to figure out what's the function that we would differentiate to get that. Well, how do we write that? We write it using this kind of a symbol. We use an integral sign, and then whatever the function that we're playing calculus Jeopardy with is, that's going to get sandwiched between the integral sign and d whatever. Usually it's x. If x is the variable of the function, like if we would plot it on an xy plane, then this would be a dx. Now if we were graphing, maybe t was our variable, then that would be a dt. Okay? But this we call this the integrand. That's the part that we're playing calculus Jeopardy with, right? So that's how we would write it. The integral of f of x dx is like saying the derivative of what equals f of x. The answer is some function, we'll call it capital F of x, plus some constant. Capital F of x is what we call the antiderivative. How come? Because why is it the antiderivative? Because it's the thing we would have to differentiate to get little f of x, right? We're not differentiating to get from here to here. We're doing the opposite. This is the derivative. We want to figure out how do we undo that derivative process and figure out where we would have started, hence the name antiderivative. Okay? This is what we call the constant of integration, and all taken together, this is called the general solution of the differential equation. That's a lot of vocabulary, but it's very simple. You already know how to do it. For example, this is how we would say this statement in calculus. The integral of cosine x dx equals sine x plus c. What does that really mean? Well, that's asking the question, the derivative of what gives us cosine x? Well, the derivative of sine x plus whatever constant you choose would return cosine x as an answer, right? Give me thumbs. Does that make sense? Okay. So therefore, that is my general solution. Okay? We can do this for all of the derivatives that you already know. For all of the derivative formulas or rules, we can just flip those around, and for free, you're going to get an antiderivative rule. Okay? So for example, what's the derivative of kx, where k is a constant? k. Okay, so how could you turn that into an integral formula? The integral of k dx, okay? The integral of k dx is equal to kx plus c. Exactly. You got one for free. Okay, we can do that for all these. What about log x? The derivative of log x is the same as 1 over x, right? That is the derivative of log x. So how could I turn that into an integral formula? The integral of 1 over x dx is equal to natural log x plus c. Give me 1 to 5. See how we're getting all these? Okay, the derivative of e to the x is e to the x. So how do you turn that into an integral formula? There you go. The integral of e to the x dx equals e to the x plus c. Now, we can pretty much interchangeably, I'm saying the word integral, but I could just as easily say antiderivative. Okay, so let's use that. I mean, it just means the same thing. If the derivative of sine x equals cosine x, then the antiderivative of cosine x dx equals sine x plus c. It's getting boring. Okay, but now we run into one that's a little trickier. Not super tricky, but we just want to be able to say it in the most convenient way. If I just turn this around directly, what would it be? Oh, yeah, okay, the antiderivative of negative sine x dx equals cosine x plus c. That's a little hokey though. We don't want to do that. We don't want to take the antiderivative of negative something. We want to be able to just plug a function into an integral formula, not a negative, right? Not a negative function. So what could I do there? Well, I mean, you could, but couldn't we even do something like this? What if we just flip this around from the beginning? What if I said, okay, well, the derivative of cosine x equals negative sine x. What if I just multiply each side of that equation by negative 1? I get negative the derivative of cosine x equals sine x. But what do we know about differentiating? If I have a constant out in front of a derivative, that's the same thing as having the constant multiplied by the function inside the derivative, right? And we know that because of our rule that we started off with, right here. That k could be outside, couldn't it? Isn't that one of our rules? We can always pull a constant outside of a function when we differentiate. Okay, so then we could just do this, right? We could take that negative and we could put it instead, we could write this as the derivative with respect to x of negative cosine x equals sine x, right? Everybody get that? This is a more convenient way for us to say this thing. Now flip this around. What do we get? Antiderivative of sine x equals negative cosine x plus c. See the advantage of that? That's a way better formula for us to use. Okay? So we've got all those. Now, what about the power rule? Here's another example of one where we're going to want to recraft this in a way where it's a little more useful to us as an integral formula. Okay? We know that the derivative with respect to x of x to the k, what's the power rule tell us? What do we do with that? If I differentiate x to the power k, k times x to the k minus 1. So if I flip that around, I would get the integral of k times x to the k minus 1 dx equals x to the k plus c. Super inconvenient. That's not a great one to use. Like, what if I wanted to do something like this? What if I wanted to calculate the integral of x to the 5th dx? Well, that's not very convenient. What would that make? What would that make K? I mean, it'd be like K in that case would be 6, I guess, wouldn't it? Right? Everybody see that? But you got to really think about it. That's not at all convenient, right? So let's think of a way we could do this that's a little better. Okay. Well, one thing we could do is we could pull that K out in front of the integral. Everybody see that? I could divide each side of my equation by K, right? And I get this. Okay, that's a little better. But even then, my general formula is in terms of x to the k minus 1. If my exponent is 5, I don't want to have to think about what's k going to be. I want to be able to just have the exponent in my formula be a single item, right? A symbol that represents, I don't want it to be something minus 1. I just want it to be something like x to the n, not x to the k minus 1. So what could I do? Ponder that, and we'll talk about it tomorrow. Okay, I'll put this first assignment up. You could get a start on it. Give me 1 second here. Uh-huh.